Hello, I am Mansi Tarani of Dayalbagh Education Institute, and today my physics topic is theoretical limits of Poisson's ratio. Before starting my topic, let me give a brief intro of Poisson's ratio. If we consider a rubber string and pull it in longitudinal direction, then rubber string would expand in longitudinal direction and contract in lateral direction. Thus, the ratio of lateral strain to longitudinal strain is known as Poisson's ratio. In order to find limits of Poisson's ratio, we would first relate Poisson's ratio with Young's modulus and Bulk's modulus. Consider a cube of side ABCDEFG of unit length. Let us consider a force F1, F2, F3, F4, F5 and F6 acts normally and uniformly in outer direction. Here force F also represents stress. Here we define two parameters as alpha is equals to increment per unit length per unit stress, which is equals to stress upon strain, that is also equals to 1 over Young's modulus, and beta, which is equals to decrement per unit length per unit stress, that is also equals to 1 over Young's modulus. Here force also represent stress because stress is equals to force upon area and it is a unit cube, so its area is 1. Consider B as an elongation point. When we apply force, the side AB would expand and BC and BF would contract. So the new length AB would be equals to 1 plus force alpha minus 2F beta, that would be equals to length of BC and that would be equals to length of CD. Thus, new volume of cube would be 1 plus force alpha minus 2F beta whole cube. On expanding this equation by binomial expression, we get 1 plus 3F alpha minus 6F beta. In order to find change in volume, we would subtract new volume by the original volume or initial volume, that is 1. Thus, we get change in volume delta V is equals to 3F alpha minus 6F beta. Now, we would find bulk modulus, which is equals to force upon volumetric strain, that is represented by K. Thus K is equals to F upon 3F alpha minus 6F beta, that is equals to 1 over 3 alpha minus 6 beta. Now we take alpha as common and we get the equation as shown. Here beta upon alpha is also equals to Poisson's ratio and 1 over alpha is equals to Young's modulus, as we have seen earlier. So the equation would become K is equals to Young's modulus upon 3 into 1 minus 2 into Poisson's ratio, and we name this equation as equation first. Now we would relate Poisson's ratio with Young's modulus and modulus of rigidity. For this, consider front face of a cube of length capital L when we apply tangential force in direction AB where CD is fixed, and thus we get AB as shared. Now we get AA dash is E and BB dash is L and the angle between them is theta. Thus, tangential stress, which is equals to force upon area, would be equals to force upon L, capital L square, and tangential strain, that is theta, is equals to L upon capital L. Now, coefficient of rigidity is equals to, that is equals to tangential stress upon tangential strain, would be force upon capital L into small l. Let alpha is equals to increment per unit length per unit strain per unit stress, that is 1 over Young's modulus as we have seen earlier, and beta equals to decrement per unit length per unit stress. Now we can observe that diagonal BD would expand and diagonal AC would contract. Thus, extension in BD due to expansion would be equals to dB into tangential force into alpha, and extension along dB due to contraction would be equals to dB into tangential force into beta. In order to find here dB is equals to L into root 2, and thus the total change would be equals to tangential force into L root 2 into alpha plus beta. If we observe in diagram, this total change would be equal to Nm, that is L by root 2. On bringing L by root 2 on other side or transposing L by root 2 to other side, we get, as we have seen, that force capital upon capital L into small l is equals to modulus of rigidity. Thus, the equation becomes, now we take 2 and alpha as common, and as we have seen earlier that beta upon alpha is equals to Poisson's ratio, so the equation would become, now we would just bring 2 alpha to the other side, and 1 over alpha is equals to Young's modulus. Thus, the final equation which we get is equals to y over 2 equals to modulus of rigidity into 1 plus Poisson's ratio. We name this equation as equation second. Now, we use both this equation in order to find limits of Poisson's ratio. From first equation, we have k is equals to Young's modulus upon 3 into 1 minus 2 into Poisson's ratio, as y and k, I mean Young's modulus and bulk modulus, are always positive quantity, and in order to make right hand side a positive quantity as left hand side, so denominator 3 into 1 minus 2 alpha should also be a positive quantity. This also means that 3 into 1 minus 2 into Poisson's ratio should be greater than 0. On transposing this to other side, we get 1 is greater than 2 into Poisson's ratio. On solving this equation, we get Poisson's ratio, the value of Poisson's ratio is less than 0.5. This is the upper limit of Poisson's ratio. Now we find other limit of Poisson ratio from equation second. From equation second, we have y over 2 is equals to modulus of rigidity into 1 plus Poisson's ratio, as Young's modulus and modulus of rigidity should be a positive quantity, and in order to make right hand side a positive quantity as left hand side, so this whole quantity should be positive. That is, this quantity should be greater than 0. On solving, 1 plus Poisson's ratio should also be greater than 0. And finally, we get Poisson's ratio as greater than -1. This is the lower limit of Poisson's ratio. Finally, the theoretical value of Poisson's ratio is greater than -1 and less than 0.5. Thank you for viewing my slide.